Okay, finding extrema on a closed interval. Theorem 3.2 states that the relative extrema of a function can occur only at the critical numbers of a function. Knowing this, we can use these following guidelines to find the extrema on a closed interval. So to find the extrema of a continuous function f on some closed interval from a to b, use these following steps. First, we find the critical numbers of the function in the interval. We evaluate these critical numbers in the interval. And then we also check out the endpoints. The least of these values is a min, the greatest is a max. So again, we have some function going on in our graph. We go from, say, endpoint A to endpoint B. We want to find the critical numbers. So we take the derivative and set the derivative equal to 0. That'll tell us the top of the hills and the bottom of the valleys, where the tangent line is equal to 0. We also check out the endpoints. Maybe we'll have a high or low at our endpoints A and B. So we want to evaluate the critical numbers and the endpoints in the original function to find our heights on the y-axis. The highest on the y-axis is the max, the lowest will be the min. The next three examples will show how to apply these guidelines. Be sure you see that finding the critical numbers of the function is only part of the procedure. Evaluating the function at the critical numbers and the endpoints is the other part. Don't forget to evaluate at the endpoints. So here in example 2, find extrema on a closed interval. Find the extrema of f of x is equal to 3x to the fourth minus 4x to the third over the interval from -1 to 2. So our first step is to find the critical numbers. And how do we do that? Is to derive it and set the derivative equal to 0. So f of x is equal to 3x to the fourth minus 4x to the third. And our derivative, f prime of x, is equal to 12x to the third minus 12x squared. So first we take the derivative, and now we're going to set that derivative equal to 0. And we want to factor, that's a minus, we want to factor this as far as we can go. What can we pull out of each of those terms? Well, we can pull out a 12x squared. If we pull a 12x squared out of the first term, we're left with a x. If we pull the 12x squared out of here, that's the entire term. We need a 1 to hold its place. So we've factored it into two factors. Now we set each factor to 0. If 12x squared equals 0, then x has to equal 0. If x minus 1 equals 0, then x has to equal 1. There are our two critical numbers. X is 0 and x is 1. I'm going to write those over to the side here. X equals 0 and x equals 1 are the critical numbers. Those are occurring inside the interval, but we might find a max and a min at the endpoints themselves. If I jump back to here. In this first example, this first graph, we did have a max value at one of the endpoints. So we want to make sure we don't miss checking those endpoints. So our critical numbers are 0 and 1. Our endpoints are -1 and 2. We want to check all four of these numbers in the original function to see which is the biggest and which is the smallest. So here we got this little box set up. Our left endpoint is -1. Our right endpoint is 2. Our critical numbers inside are 0 and +1. Now to make it easy, if you want to evaluate these on the TI-89 calculator, go to the Y editor and input the original function f of x. Go to table set and make sure it is set to ask mode. And then go to the table itself and plug in these values. If we plug -1 into the original function, we get an output of 7. If we plug 0 into the original function, we get an output of 0. If we plug 1 into the original function, 3 minus 4 is -1. And if we plug 2 into the original function, we get an output of 16. So we look across our values. The highest is 16. That's our max. Of all the numbers, our lowest is -1. That's our minimum value. And we can look at this graphically too. Here is the graph of the function. So our endpoints were from -1 to 2, and there were our values 7 and 16. And we did have a critical number here occurring at the origin. We do have a slight little horizontal tangent line there. And then we do have a little dip down here. That is our minimum value. At y is -1, our max value did occur at the endpoint. Example 2. Now our function is f of x is 2x minus 3x to the 2/3. And our interval is -1 to 3. So we begin by differentiation. F prime of x. The derivative of 2x is 2. And the derivative here, 3 times 2/3 will be 6/3, or 2x. We drop the exponent by 1. 2/3 minus 1 is -1/3. And let's rewrite that without the negative exponent. 2x to the 1/3, or that is the third root of x. Now we want to know where this derivative is either equal to 0 or when it does not exist. You know, when would this not exist? When would we run into trouble here about this not existing? We have a denominator with a variable in it. We never want to divide by 0. So if even just this piece of the function is a divide by 0 situation, the whole thing blows up. So it is not going to exist at x equals 0. That's one of our critical numbers. Overall, when would this entire thing equal 0? 2 minus what equals 0? Well, 2 minus 2. When would this term equal 2? Well, the numerator is already 2, so when would this denominator equal 1? Well, that would occur when x is equal to 1. The third root of 1 is 1. 2 divided by 1 is 2, so 2 minus 2 would equal 0. So our other critical number is when x equals 1. So we have our two critical numbers. We know that when x is 0 and x is 1, something's going on. We also want to check out our endpoints of the interval, -1 and 3. So again, this is easiest done on the calculator. Go to the y editor and input the original function, 2x minus 3x, and remember to do this in the calculator. You want to do x up caret for the exponent, and this exponent, since it's rational, you need parenthesis. 2 divided by 3, close parentheses, enter. Go to the table and input these 4x values, and let's see what output comes out. When we plug in our left endpoint, -1, we get an output of -5. When we plug 0 into the function, out comes a 0. When we plug in the critical number 1, we get a value of -1. And when we plug in our right endpoint of 3, we get approximately -0.24. So now we just check each of them out. What is the lowest of all of them? Well, that's our left endpoint, -5. That's our minimum value. Which of those is the highest? Well, 0. Everything else is negative. So there's our max value. So our min occurred at an endpoint. Our max was one of the interior critical numbers. And here's a graph of this function. So it sort of starts out as a line coming up to the origin, and then we got a little curve going underneath it. You know, our interval was from -1 to 3, so here at our left endpoint we do have our lowest value, -1, -5. And then if we scan the entire function, we see our high point is here, right at the origin, 0, 0. So now we got to do one with some trig functions in it. Here we got a sine and a cosine going on. So our left and right endpoints are 0 and 2 pi, and we want to start this off by taking the derivative, f prime of x. What's the derivative of 2 sine? Well, that's going to be 2. Derivative of sine is cosine. Minus the derivative of cos of 2x. Well, the derivative of cos is negative sine of that same 2x, and since we have an inner function, we need to apply the chain rule. The derivative of this inner function 2x is just a 2. So let's collect some stuff up here. We're going to have our 2 cos x. These negatives will cancel each other out and become a positive. And let's move this 2 to the front. Plus 2 sine of 2x. And we want to set this equal to 0. Now this would be doable, but to make it a little easier on ourselves, if we look at this part right here, the sine of 2x, if we remember back to pre-calc, if we have the sine of 2x, we can replace that with 2 sine x cos x. That's just a trig identity from trigonometry. So if we do that here, if we pull that 2 out, we're going to multiply it by the 2 that we already have in front. So that 2 times 2 is 4, and now it's sine x cos x. And that's equal to 0. And now that I look at each term, I see something can be factored out. Well, from the numbers, I can pull out a 2, and I can pull out a cos x. So I'm going to pull a 2 cos x out. If I pull that out here, that's this entire term. I'm going to need a 1 as a placeholder. If I factor a 2 out of here, out of this 4, I'm still going to have a 2 remaining. And I pulled out the cos term, so the sine term remains. And that is equal to 0. So we've derived it. We have set we've set the derivative equal to 0 and factored it. Now we set each factor to 0. When 2 cos x equals 0, we can divide by 2, and that's gone. And then we just have cos x equals 0. Where does cos of x equal 0? Well, if we think back to the unit circle, that's going to be occurring on the y-axis, positive and negative. So that occurs at pi over 2 and at 3 pi over 2. For our second term, we set this term equal to 0. 1 plus 2 sine x equals 0. I'm going to subtract 1 from each side and then divide by this 2. So I'm going to have sine x equals negative 1/2. So pull out the old unit circle. Remember that sines are the y values. Look around the unit circle. Remember, sines are y values, so it's only going to occur under the x-axis. And where does that occur? That happens at 7/6 pi and also at 11/6 pi. So now we have 4 critical numbers, and we have our endpoints that are all going to need evaluated. Again, this is a real good one to do on the TI-89, and make sure you are doing this to the original function. So plug this original function into the Y editor, make sure you are in ask mode, and we're going to plug these in there and see what values pop out. So for the left endpoint, when we plug 0 in, output negative 1. For pi over 2, I forgot to white it out of the notes, our value is 3. For the 7/6 pi, we get a value of negative 1.5. For 3/2 pi, we get a value of negative 1. For 11/6, we get a value of negative 3/2. And for our right endpoint at 2 pi, we have an output of negative 1. So let's look for the biggest number of all. Well, all those are negative except right here. We have our max at 3. What about our lowest value? Well, negative 1, negative 1, negative 1.5, and negative 3/2. These are basically the same thing. So we sort of have a tie in the race for our minimum. Negative 1.5 and negative 1.5 are both mins. And if we look at the graph of this, here we go. So here's our function. You know, we got a couple curves going on, and we do easily see that our max value is right here, the top of this really tall hill. That occurs at pi over 2, and our y value is 3. When it comes to the min, we have a couple dips down here, and these valleys, the bottom of these valleys, occur at exactly the same height on the y-axis, negative 1.5. And that is the end of section 4-1, our first applications of these derivatives. And just for a recap, we want to find the critical numbers, where stuff is happening, where the function has a hill or a valley. So, take the derivative. Set the derivative equal to 0 to find the critical numbers. Evaluate those critical numbers and the endpoints in the original function to find our values on the y-axis. The least of these is the min, the greatest is the max.